Welcome to this video. This is topic 15 of Edexcel International LFL Chemistry of Unit 4. This is basically the last topic of Unit 4 and kind of like an introduction to organic chemistry in A2. So this topic 15 is divided into 4 chapters. Number 1 being topic 15A, which is isomerism and chirality. Chapter 2 is topic 15B, which is carbonyl compounds. So these first 2 chapters are quite small and easy. And then topic 15C, this is carboxylic acid and derivatives. This is a really important chapter if you want to do good in Unit 4. And lastly, the 4th chapter is enamel spectroscopy and chromatography. This is also really small and moderately easy, not extremely easy. But 15C will be the main nemesis in organic chemistry of Unit 4. So without further ado, let's get right into it. So isomerism and chirality. No introduction needed for isomerism. We already know what isomers and isomerism is from our DCSE and AS level, but chirality is something that we may not necessarily know about. So this stuff. We will read about this in this video. And so classification of isomers. Most of us have probably seen map diagrams like this for isomers. So I think it really helps understand the branches of isomerism and the types of isomerism. So isomers, they are of 2 types. There are 2 types of isomers: structural isomers and stereoisomers. Okay, so under structural isomers, there are carbon chain isomers, positional isomers, and functional group isomers. And all of this stuff we know from AA. And under stereoisomers, there are geometric isomers and optical isomers. And all of this stuff we know from AA. Only the optical isomerism bit is from A2. So under carbon chain isomers, basically same number of carbon atoms, same molecular formula, same functional group, but these are such compounds that they will have different branching, so their main chain will be different. The main chain length will be different, everything else is the same, so their molecular formula is the same. So these are called carbon chain structural isomers. And positional isomers, also the same number of carbon atoms, same molecular formula, same functional group, but the position of the functional groups are different, such that you could have butan 1-ol and butan 2-ol. So the OH hydroxyl functional group is joined to different carbon atoms, different number of carbon atoms, different numbered carbon atoms to say. So that is that. And then functional group isomers. So these are basically also structural isomers and same number of carbon atoms, same molecular formula, but the difference is they have a different functional group. So regardless of having the same molecular formula, they are still having different functional groups. So 2 examples of functional group isomerism that you really need to know are aldehyde and ketone and carboxylic acid and ester. So this is carboxylic acid, propanoic acid, 3 carbon, and this is methyl ethanoate. This is an ester. So if you write find out their molecular formulas, they will be the same, but their functional groups are different. And this is propanol and propanone. So aldehyde and ketone. So same molecular formula, but the functional group is different. Molecular formula is same. So that is that. Functional group isomerism done. Now stereoisomerism, geometrical isomerism under that. So cis-trans and EZ or easy isomers. So just like it sounds easy, it actually is easy. So, but one thing you must know that from AF, if I recall correctly, the definition we read, it read something like geometrical isomerism occurs in carbon-carbon double bonded compounds, such as in alkenes. But we are building up on that definition quite a bit in A2. So let's look at the new definition. So geometrical isomerisms or geometric isomerisms, these occur in alkenes, cyclic compounds, as well as compounds with square planar and octahedral shape. So all of these are organic compounds that are eligible to be geometric isomerism, eligible to exhibit geometric isomerism. Give me a minute, I'll need to drink some water. Come back. So these number 1 and number 2 points, these are marking points for the exam question. It would be like, explain how compound X exhibits geometric isomerism. So these are the following marking points that I have taken from marks, obviously. So the first marking point goes, so there must be restricted rotation around the bond, such as the carbon-carbon double bond in alkene due to pi bond. So thanks to pi bond, we got restricted rotation. And each of the double bonded carbon atoms, so this and this, must be bonded to 2 different groups of atoms. So this carbon atom over here is bonded to a hydrogen and bonded to a methyl group. So it is actually bonded to 2 different groups of atoms. Likewise, same for this carbon atom. So the requirements to fulfill the definition is there. So now What about cis-trans and EZ? So to understand cis-trans and EZ, we need to understand what do we mean by priority. So these double bonded carbon atoms here are obviously have to be bonded to two different groups of atoms. So since they are bonded to two different groups of atoms, these groups of atoms that we are talking about, they must have different molecular masses. So CH3 and H. This is 15, molecular mass is 15, and its relative atomic mass is 1. So 1 and 15, obviously different molecular masses. So what about priority? So we are saying that the higher the molecular mass of bonded group, these groups over here, the higher the priority. And for exhibiting cis or Z isomer to be a cis or Z isomer, these high priority groups, so the higher the molecular mass, the higher the priority. This is the higher priority group. Okay, this is also the higher priority group. So for cis or Z isomer, the higher priority groups have to be on the same side. Yes, same side. And for trans or E isomer, this higher priority groups have to be on different sides. So if CH3 is here, one CH3 is here. If another CH3 was here, then they would be trans isomers or E isomers. So as easy as that. So now looking at some A2 level material. So this is octahedral. Yeah, this is a cyclic compound, obviously. So definition, check. Octahedral or not? Yeah, check. So this carbon atom and this carbon atom, these are the only two carbon atoms that are bonded to two different groups of atoms. Rest of the carbon atoms are bonded to same two hydrogen atoms. So we only have to talk about these two. So yeah, the high priority groups, obviously the ones with more molecular mass, chlorine, chlorine, they are on the same side. So this is cis or Z. But here, on the contrary, the high priority groups are on different sides. So this is E or trans. Okay, so that is that. And so octahedral done, cyclic done. Now the square planar. So this cis and trans platin, I like to call them FAQ. FAQ stands for frequently asked questions. So in all of the October papers, before the new spec, stuff on this used to come all the time. So cis and trans platin questions would come even in Unit 4 all the time, although this is more of a Unit 5 thing, transition metal complexes, falls under the topic. So, but regardless, this stuff comes in Unit 4 as MCQ. So what you really need to do, or need to be able to do, is that you must be able to identify which one is cis and which one is trans. That is all you need for A2. So for identifying cis and trans, obviously there is a central group, atom, platinum atom, bonded to four different groups of atoms. So angle between similar groups. This stuff is little different than this. So if the angle between similar groups, such as chlorine similar group, NH3 and H3 similar group. So if the angle between the similar group is 90 degrees, then we have got the cis isomer of the square planar compound, square planar shaped compound. So this Cl, this 90, this another 90, another 90, another 90, overall 360. So if the similar groups are separated by a 90 degree angle, then the square planar shaped compound, organic compound that we are talking about, will be of the cis isomer form. And if the angle between the same groups or similar groups is of 180 degree, then they are of the trans form. So that is that, done in 10 minutes. So, okay, now A2. Now the more important stuff. So optical isomerism. All of these are done. Now this stuff. So brace yourself. So optical isomerism, we define this. So it is, we can obviously define isomers. So it is the existence of compounds with the same molecular formula, yes. But for optical isomer, also the same structure formula, different arrangement of atoms or groups of atoms in three-dimensional space. So this is the definition. The another part of that is these are organic compounds that interact differently with the plane of polarization of plane polarized light. So what is plane polarized light, if you ask me?
Electromagnetic beam of light is composed of electromagnetic waves that vibrate in all possible directions perpendicular to its path. Certain materials, such as plastic Polaroid film, have the property of absorbing all the waves except one that vibrates in a particular plane. Light that consists of waves vibrating in only one plane is referred to as plane polarized.
So that is done. So basically, we are saying that light that vibrates in only one plane, say the vertical plane only, and the horizontal components are cancelled by some means or forms. So light waves that vibrate in only one plane is called plane polarized light. Okay, so that is Unit 2 physics stuff. A lot of students who want to do medicine, some of them tend to not take physics in A level. So for AS physics, that stuff is covered in AS physics. So I decided to play the video for those who don't have physics. So that is that. Plane polarized light is done. Light is obviously a wave, and so light is a wave and is an wave of the electromagnetic spectrum. So that is stuff you already know. So optical isomerism, this results from a chiral center in a molecule with an asymmetric carbon atom. So a chiral center and an asymmetric carbon atom, essentially we are talking about the same thing. This is basically when a carbon atom is obviously at the center and it is bonded to 4 different groups of atoms. That is what makes a carbon atom asymmetric. Okay, so that is that easy stuff. And optical isomers are called enantiomers. Just treat it as simply as that geometric isomers can be called cis-trans isomers. Likewise, optical isomers are called enantiomers, as easy as that. Give me a minute. And again, we have defined optical isomers. Now, let's see if we can identify optical isomers. I don't know. Okay. No. So this is organic compound and another organic compound we got. So let's look at this over here. So this is an organic compound. This is obviously the chiral center that we were talking about. And can we say that this chiral center is asymmetric? Well, we can say that because this chiral center or the central carbon atom is bonded to a methyl group here. So a methyl group here, and OH group here, a hydrogen atom here, so 3 bonds, and the 4th bond is another carbon atom that is double bonded to an oxygen and an OH, so a carboxylic group. So this center, this chiral center, consists of an asymmetric carbon atom because it is bonded to 4 different groups of atoms. So that is how we identified an organic compound who exhibits optical isomerism. So enantiomers. So an enantiomer is an isomer that is optical isomer that is non-superimposable on its mirror image. Okay. So this is an organic compound and this is its mirror image. So no matter how many different ways you desire to arrange this in, you can never have this arranged in such a way that this will completely impose on top of this. Okay. I will explain that a bit later. Show that a bit later. Okay. So enantiomers are therefore called optically active. So what is actually optically active mean? So being optically active means that compounds, these are optically active compounds, are compounds which can rotate the plane of polarization of plane polarized light. How so? So this was the source of light wave vibrating in all these directions. But after passing through this Polaroid filter, these only vibrated in the vertical plane. And in this container here, we got some D enantiomer, we got some optically active compound or some optical isomer in this container over here. And so these vertically rotating or vertically plane polarized light, when it passed through this container of this optical isomer, its plane of polarization was rotated by an angle. Plane of polarization was rotated by an angle. Plane of polarization was rotated by an angle. So here to here. So that is what we are saying. So there are 2 types of enantiomers. The positive enantiomer is called dextrorotatory. You do not need to know these terms. Just saying positive and negative enantiomers is just as fine. So positive enantiomers rotates the plane of polarization of plane polarized light in the clockwise direction. So like this. And negative enantiomer rotates the plane of polarization of plane polarized light in the counterclockwise or anti-clockwise direction. So like this. So this is the positive enantiomer and this is a negative enantiomer. And we will never be asked which one is positive, which one is negative. This is just randomly assigning this to be positive and this to be negative, because if this is positive, this has to be negative, because these two can never be superimposed on each other. So they are obviously enantiomers. And if this was positive, this would be negative. Okay. So to help you understand this line over here more clearly, we will look at this example. So this is a mirror, and this is when these mirror images, this image and this image, are superimposable on each other. So achiral. Okay. If they are superimposable, they are achiral. So if I rotate it like this, let me have a thick. So if we rotate it like this, then this can be superimposed on this. This can be superimposed on this. They will be completely overlapping each other. But if I rotate it like this, these two will never superimpose. So they are non-superimposable mirror images. Just look at this. They are achiral objects, so these two can be superimposed, completely overlapping each other. But if these two are superimposed, they will look like this. They cannot be superimposed. They cannot overlap each other completely. So that is that. So now you understand that when you see yourself in the mirror and the person that will be looking back at you, if that person is to be dragged out of the mirror and overlapped on top of you, you two will never overlap each other completely. So think of it as easy as that. So please, now looking at the piece of these enantiomers or optical isomers. So in terms of properties, chemical and physical properties, they have identical chemical properties. Yes, same physical properties, so same temperatures, boiling temperatures, and same solubility. But they differ in two different ways. The first way is quite obvious, that they rotate the plane of polarization of plane polarized light in opposite directions. So this is one. And another is they have different biochemical reactions. So when you get to unit 5, you will understand that isomerism. Why is isomerism a big deal? Because okay, I'll talk about that later. Let's star mark this. I will explain this just a little bit down here in the third page. And now we are in the second page. I will explain this. So the thing to note is that the angle through which the plane of polarization is rotated depends on two things. Okay. Which angle again? This angle. So this angle depends on two things. The first is the nature of the enantiomer, i.e. the type of compound exhibiting the optical isomer. So whether this or this compound, which compound is exhibiting optical isomerism, that determines the angle. Another is the concentration of the enantiomer. So more the enantiomer of a certain type, more of the positive means more the rotation in the clockwise direction. More of the negative, more the rotation in the anti-clockwise direction. And if these two are of the same concentration, so square bracket, what does that mean? Square bracket means concentration, A2 level, basic stuff. So if their concentration are the same, then the angle through which this plane is rotated is 0. So the changes in the rotation of plane of polarization will then be cancelled out. And now we will look at that. So what is a Racemic mixture? So Racemic mixture, it is also known as a Racemic. Basically a solution mixture containing equimolar or equal amounts or most amounts of positive and negative enantiomers. Okay, so in a Racemic mixture or a Racemic, the changes in plane of polarization are cancelled out. Hence, a Racemic mixture is optically inactive. So if the changes in the plane of polarization are cancelled out, then there will be no rotation in the plane of polarization of plane polarized light. So if there is no rotation, how can your compound be optically active? It has to be optically inactive. Because these two, if one was in higher concentration than the other, then a solution of them is the plane of polarization. So then they would be called optically active. But if they are of the same concentration, there would be no change there will be no net change. So they will be then called optically inactive. So just highlighting this definition over here. So again, this bit to this bit. So one really important question, MCQ, that comes in exams is, they will give you a skeletal formula of a compound like this, and they will ask you to either identify the number of chiral centers, or they will another MCQ of type B. So that was type A. And MCQ type B will be they will ask you the number of optical isomers. So the number of chiral centers or the number of optical isomers. Either of these MCQs they will always ask. So let's see how we can easily identify them. So this is obviously a carbon atom. Carbon, 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 CH3, CH2, CH2, because from a point, if we got one bond over here, one bond over here, then the remaining two bonds of the carbon, because carbon can form four bonds, so the remaining two bonds must be hydrogen, unless shown otherwise. So that is how easily you can read this whole structure. So carbon, 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 and oxygen, oxygen. So this carbon bonded to two different hydrogens, so this is not chiral. This carbon bonded to two different hydrogen, not chiral. This carbon is bonded to a chain on this side and another chain on this side. So this direction and this direction, these two bonds are not the same, because this bond extends to a carbon which is bonded to a double bonded oxygen, but this bond extends to a carbon which is bonded to two hydrogens, two same hydrogens. So this bond and this bond are not the same. So what I was saying, this bond of this carbon and this bond are not the same, and another bond would be hydrogen and another bond is OH. So four different bonds, four different groups of atoms. So obviously this is a chiral center, because the center is bonded to four different groups of atoms. But this carbon over here, star, so bonded to a double bonded oxygen, bonded to this side and bonded to this side. And you may ask, so why did I not put a star mark on here? Because a carbon can form four bonds. And so this carbon over here is double bonded to an oxygen. So it only has two more bonds. This bond and this bond. This carbon is not even bonded to four different groups of atoms. How can it be chiral? Because to be chiral, you need to be bonded to four different groups of atoms. This one bonded to two hydrogens, so this ain't chiral. Only this and this. So only this and this are chiral. Okay, so two chiral centers. So one easy trick to solve MCQs, if they ask you the number of optical isomers, so you will just put this formula. Number of optical isomers is 2 to the power n, where n is the number of chiral centers. So if there are two chiral centers, n will be 2, so 2 to the power 2 is 4. So there will be 4 optical isomers. Okay. So if I have to explain that stuff a little more, that would be like, this chiral carbon will be responsible for creating a positive enantiomer and a negative enantiomer. So 2 from this, 2 from here. And this chiral carbon will also be responsible for creating 2 more enantiomers. So 2 more from this. So total is 4. So that was a little bit of explanation there, but that is not needed. So now we will look at chirality and mechanism. Okay, kind of like applied chemistry, and we are at this part over here that after reading through this, I will explain you the biochemical reaction part. So chirality and mechanism. So when an optically active organic compound, yes, this is optically active, 4 different groups of atoms, undergoes a nucleophilic substitution reaction, the formation of an optically inactive product is the evidence of an SN1 mechanism. So that is how we can identify an SN1 mechanism, detect an SN1 mechanism. So while the formation of an optically active product is the evidence of SN2 mechanism. So formation of an optically inactive product, evidence of SN1, formation of optically active product, evidence of SN2. So let's see why is the product of SN1 mechanism optically inactive. So SN1, halogen alkane, bromo alkane over here. So this carbon between heterolytic bond fission occurs. So we get a carbocation intermediate, a trigonal ternary intermediate. So, and once this intermediate is formed, the OH nucleophile can attack this carbocation from either side. So this OH nucleophile can attack this carbocation from either this side or this side or this side, and from any side. Okay. So this carbocation intermediate could be attacked by the OH nucleophile from any side, and attacking from this side were to result in formation of a positive enantiomer, then attacking from this side would be resulting in the formation of a negative enantiomer. So that is why we are saying that therefore this will result in a Racemic mixture forming. So both the positive, we are just randomly assigning one to be positive and one to be negative, because we do not have to know which one is positive and which one is negative, rather the knowledge of it, rather the understanding of it. So there it goes. So positive and negative, both the enantiomers will be formed in equimolar quantities. Because the Racemic mixture forms, there will be no optical activity in the products. So since no optical activity, this angle over here will be 0. There will be no angle. All of this will go unrotated. So in SN1, there is lots of optical activity. The planar carbocation, diagonal planar carbocation intermediate can be attacked by OH ion from either side, resulting in equal concentration of both the enantiomers. It's Markheim level detail. This much detail is not even required. This is enough. This is from Markheim. And in SN2 mechanism, the no carbocation intermediate is formed, rather a transition state complex is formed. And don't ignore this stuff. This is extremely important. Comes all the time in MCQ. This stuff. They will always come in MCQ. This page, third page. So in the SN2 mechanism, no intermediates are formed, and the reaction occurs via transition state. So this is the transition state intermediate. No carbocation intermediate over here. So if the reaction was chiral, yes, this is obviously a chiral. This is obviously a optically active reactant of halogenoalkane. So during the reaction, the opposite enantiomer would form. I will explain this stuff. No chemistry teacher on planet Earth, you name it, no internet notes will explain this stuff, but I will. So if the reactant was chiral, then during the reaction, the opposite enantiomer would form. How is that so? So analyze this stuff. This carbon-bromine bond breaks heterolytically, and you get and at the same time OH nucleophile attacks. So these two, the heterolytic bond fission and nucleophilic attack, both occur at the same time. So that is why we get the transition state complex with the partial bonds. These are not actually true bonds, so partial bonds. This would break away and this would form more strongly in this here. So what you can notice is that if you compare only this and this, you will see that the CH3 was on the left hand side over here and it is in the right hand side over here. Same for, but the fluorine is same, and H was in the right hand side over here but left hand side here. So if we were to erase this stuff and put a mirror in front, then would you not say that if this was positive, this is negative? Would you not say there is some form of inversion? So yes. So if the reactant was chiral, then during the reaction, the opposite enantiomer product would form. If reactant was positive enantiomer, product would be negative enantiomer, and vice versa. So this is what we call inversion. So the explanation goes like this. So in SN2 mechanism, there is a change in optical activity or inversion. SN1, there is loss of optical activity. SN2, there is change in optical activity. So the OH nucleophile attacks the slightly positive carbon. Yes, slightly positive carbon from the side opposite to the halogen. So not from this side, but from this side. Due to repulsion from lone pair on the halogen, the single optically active product is formed where the optical isomerism is inverted. And we have already read this stuff. So optical isomers is done. So isomerism and chirality finished with this. Now, in this nucleophilic substitution reaction, there may be other reactions also forming. Yes, there is actually another reaction. What was that reaction? Yes, you will know about that later on in topic 15b. So this was 15a. In 15b, you will learn about another reaction. This is nucleophilic substitution, and that will be nucleophilic addition. Okay. So in the nucleophilic addition reaction of carbonyl compounds, you will also see that mechanism also results in changes in optical activity. So nucleophilic substitution and nucleophilic addition in the next chapter. So these are examples of two reactions that result in some changes in optical activity of our mixture. So how do we relate that to different biochemical reactions? So the thing is, in the laboratory or pharmacies, so what pharmacists do is that they carry out different reactions, let it be nucleophilic substitution or nucleophilic addition. So what they do is they carry out different reactions, organic chemical reactions. So in these reactions, different products are formed, and maybe half of the products are of the positive enantiomer and half of the products are of the negative enantiomer form. So what pharmacists do is basically they want to prepare or create drugs. So positive and negative enantiomer form of a drug are not necessarily of the same effectiveness. The positive enantiomer drug may be more effective than the negative one in order when it comes to treating a particular disease. So what pharmacists want to do is that they want to manipulate these reactions that occur in their pharmaceutical labs. They want to manipulate these reactions in such a way that they will get their desired enantiomer in more desired amounts. Okay. So their drug yield will increase. So the yield of their drug will increase. Their cost in separating the other enantiomers, for example, the negative, or could be the positive. If the negative is required, then their cost of separating the positive form will be reduced, because there will be no need to separate the positive form if the positive form cannot form at all. Okay. If they are desiring the negative form for creating a particular medicine or drug. So So that is why we are saying, so why is that important? Because as I said, positive and negative forms, they have different biochemical reactions. They have different effectiveness in treating diseases such as cancer. Okay. So this concludes topic 15A. And I will put an exam question right now. So we are back, and the exam question that I was talking about is this one. Although this exam question has never appeared in Edexcel, the exam questions that do appear in Edexcel, I have covered them in the lecture video. So no need for them, I guess, but try this one over here. Pause the video and see if you can do this. Okay, so here is the marking. So thank you for watching this video if you made it this far, and please share, subscribe and like.